For this, we consider this product and multiply this this product to this equation. Okay, so multiply this in this equation. So what will be the first term? First term will be C1 times pre-multiply. Let's say pre-multiply. So C1 times this product X1, C2 times this product X2, dot 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 Cn times this product into Xn. And on the right hand side we have 0, so the product on the right hand side will be 0. Okay. Now look at this this term. Look at each of the term in this expression. So first term in this expression is this one. Okay. So if this so you multiply so you can write this term, the first term, as a lambda 2I, a minus lambda 3I, a x1 lambda and x1. Okay. This term ax1 is lambda 1 x1 because lambda 1 is the eigenvalue corresponding to the eigenvector x1. Okay, so you get this quantity from the last term of this product. Now lambda 1 minus lambda 2 is a constant, so you can repeat this operation and ultimately you will have lambda 1, this first term will be equal to lambda 1 minus lambda 2, lambda 1 minus lambda 3, so on to lambda 1 minus lambda n. Okay. So we have this first term is equal to this quantity. Okay, times C1. Now how about the second term? So for the second term onward, this is the second term here. In the second term, we see that we have the vector x2, and we also have a minus lambda 2I. So when x2 is multiplied by a minus lambda 2I, this will become 0 because lambda 2 is an eigenvalue corresponding to the eigenvector x2. So this term will be 0. The second term will be 0. And similarly, third term and so on, the nth term, all the terms will be 0. Okay, so except the first term, all the terms will be 0. So therefore, we can say that we have C1 times lambda 1 minus lambda 2 times lambda 1 minus lambda 3 times dot 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 times lambda 1 minus lambda n, and since is equal to 0. Since lambda 1, lambda 2, lambda 3, so on, lambda n are distinct eigenvalues, therefore the only possibility for this product to be 0 is that C1 is equal to 0. So you get C1 is equal to 0. Okay. Right. So now we are able to prove C1 is equal to 0. We can repeat the same argument for C2. Now for C2, we will use a different product. If you see that in the beginning, we started with this equation. And we multiplied this equation by this product, pre-multiplied by this product. And here in this product, you see that we wanted to make C1 is equal to 0. So that is why A minus lambda 1 I is not present. Okay. When you want to prove that C2 is equal to 0, what you do is you repeat the same process and replace this by A minus lambda 1 I, A minus lambda 3i. So for C2, A minus lambda 2i will not be present in this product. A minus lambda and I. Okay. If you repeat the process, similar calculation will give you C2 is equal to 0. Fine. Now, if you want to show that C3 is 0, you simply multiply. You do not include A minus lambda 3. So you have A minus lambda 1i, A minus lambda 2i, A minus lambda 4i. You will not include A minus lambda 3i. A minus lambda n I. Okay, so with this, you will get C3 is equal to 0. And so that means if you want to show Ci is equal to 0, you will not include A minus lambda I into the identity matrix I in the product. Okay, so that only the Ci term remains non-zero. Ith term remains non-zero in when you multiply this product in the equation, and all other terms except the ith term are 0. Okay, and then from there you can show that Ci is 0. Okay, so with this process, by repeating this process again and again, one can show that each of these Ci's are 0. Okay, so that means we started with the linear combination of the vector x1, x2, xn, the eigenvectors x1, x2, xn, and we are able to show that the coefficients Ci's are 0 for all I. That C1 is 0, C2 is 0, C3 is 0, so on, Cn is equal to 0. Okay, so this means that x1, x2, xn are linearly independent. Okay, so this is a very useful result. If you have n distinct eigenvalues, then the eigenvectors of A will be linearly independent. And from the previous theorem, we can say that A is diagonalizable. Okay, so if you want to show that A is diagonalizable, you just calculate the eigenvalues. If the eigenvalues are distinct, then immediately you can say that A is diagonalizable. If the eigenvalues are not distinct, then you cannot say anything about diagonalizable. It can be diagonalizable, it can be non-diagonalizable. Okay, so if eigenvalues are not distinct, you have two or more eigenvalues which are equal, then you have to identify eigenvectors which are linearly independent. If you are able to identify eigenvectors which are linearly independent, then from the previous theorem, from this theorem, you can say that A is diagonalizable. Okay. If eigenvectors are not linearly independent, then A is not diagonalizable. Is this fine? Any question here?
So I didn't get that how you reach that equation C1 bracket lambda minus lambda 1 minus lambda 2 into lambda 1 minus lambda 3.
You did not understand it.
So fifth line of the proof, so this
Right.
equation C into lambda 1 minus lambda 2.
So just consider two vectors and then you can write everything for n vectors. So you have C1 x1, C2 x2, right? You have two vectors, that means two eigenvalues. Right? This will hold. Now you
Yes,
start
sir.
in a combination and then you multiply this equation by A minus lambda 2i. So what will be the first term? C1. C1 is constant, so you can write C1 A minus lambda 2 I times x1 plus C2 A minus lambda 2 I times x2 is equal to 0. Do you agree with this?
Yes, sir.
Now look at the second term. The second term is 0 or not?
Yes, sir, it is.
It is 0 because ax2 is equal to lambda 2 x2. So this term is 0. How about the first term? First term will be
Yes,
C1 ax1 minus lambda 2 x1. And what is ax1?
lambda 1 x1.
Yes. Ax1 is lambda 1 x1. So you can take x1 outside. So you can write lambda 1 minus lambda 2 x1 is equal to 0. Fine.
Okay, sir. Yes, sir.
And lambda 1 and lambda 2 are distinct. This is what we have said in the beginning. These different eigenvalues. So lambda 1 and lambda 2 are not equal. So the only possibility for this to be 0 is C1 is 0 because x1 also cannot be 0. X1 is an eigenvector, right?
Yes, sir.
So eigenvector cannot be 0 because you are always looking for a solution, non-zero solution, which will satisfy the equation Ax is equal to lambda x. So by definition
Yes.
of eigenvector is not 0. So eigenvector is not 0. Lambda 1 and lambda 2 are not equal. So the only possibility is that C1 is equal to 0. So from there you get C1 is equal to 0. Right?
Okay, sir. Yes, sir.
Now you extend this idea to the n vectors. Okay?
Okay, sir.
Yeah, so this is the idea. Is this fine?
Yes, sir.
Now similarly you can use multiply a minus lambda 1 x, a minus lambda 1 I to both the sides so that the first term will become 0 and the second term will give you C2 lambda 1 minus lambda 2 into x2 is equal to 0. And from there you can get C2 is equal to 0. Right. So just extend everything to the n vectors. And the extension is very simple because you just have to like somehow readjust the terms here. When you extend this, you just have to readjust the term. Basically you use this relationship. Right. This relationship will be used so that you can, for example, if I multiply uh, when you multiply this term, you have for the second term, in fact, this will be used. When you have this one, you see that the vector x2 is sitting at the end of this product in this term, right? This is x2. So somehow you have to bring this x2 with this expression a minus lambda 2. And this inequality will help you. This equality will help you to bring this inside. So that means you can interchange the product. The initial product is a minus lambda 2i into a minus lambda 3i and dot 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 a minus lambda ni. So you can write this as a minus lambda 3i dot 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 a minus lambda ni, and lastly it will be a minus lambda 2i, and then you have x2. So then this x2 will come inside, so you will have a x2 minus lambda 2i, and that makes the product 0. Are you following?
Yes, sir.
Because of this relationship, you can interchange the product. A minus I a minus ai into a minus bi. Reverse this product, the order of the product. So you will get a minus bi, and then multiplied by a minus lambda, a minus ai. Okay, so along with this inequality, you apply the same argument. This equality, you apply the same argument. Any further question on this theorem?
No, sir.
Okay, so now we go to this example 16. So this says that the matrix A is diagonalizable. So what do you will do first? You will calculate the eigenvalues. So calculate the eigenvalues. The eigenvalues, you know how to calculate eigenvalues now. So when you calculate the eigenvalues will come out to be this. First eigenvalue is 0, second eigenvalue is -4, and third one is 3. And these eigenvalues are distinct. Right? These are distinct eigenvalues. So from the previous theorem, if you have n distinct eigenvalues, then the eigenvectors are linearly independent, and therefore A is diagonalizable. So use this theorem, so you can immediately say that A is diagonalizable. Fine. Now the next part of this question says that also find an invertible matrix P such that P inverse AP is a diagonal matrix. Okay, so how will you calculate this P? More or less we have given I've given the hint in some proof of this theorem, I think somewhere here, how to calculate this matrix P here. So this matrix P will you can form this matrix P with the help of linearly independent eigenvectors. So in this example, the eigenvalues are distinct, so therefore eigenvectors will be linearly independent immediately. So just calculate the eigenvalues for each of the eigenvectors. So just calculate the eigenvector for each of the eigenvalues here. So if lambda, so first eigenvalue is 0, corresponding to this eigenvalue, you can calculate the eigenvector, which will be this. Second eigenvalue is -4, corresponding to this. The eigenvector is this one, and the third eigenvalue is 3, corresponding to this. The eigenvector is this, and you can check that these eigenvectors are linearly independent, which is obvious because the eigenvectors are distinct. So from the previous theorem, since eigenvalues are distinct, so therefore eigenvectors are linearly independent. Now with the help of these eigenvectors, you can form the matrix P. So matrix P will now be, you take the first column as the first eigenvector. This was the first eigenvector. Substitute this value here to form the first column. 1, 6, minus 13. Second column, this will be constructed with the help of the second eigenvector, minus 1, 2, 1. And third column of P is the third eigenvector, 2, 3, minus 2. Okay. And these eigenvectors are linearly independent, so it will be invertible because all the three columns of P are linearly independent. And columns are linearly independent means that the rank of P is equal to the order of the matrix. In this case, the rank of P will be 3, which is the order of the matrix. And if the rank and the order are same, then the matrix is invertible. So P inverse will exist. So you can calculate P inverse. You know how to calculate P inverse. So when you calculate P inverse, this will come out to be this. And then you can check P inverse AP. This product will come out to be, when you do this product will come out to be D. Okay, and this D is the diagonal matrix, this one. Now you can see that you just recall this result, the result that we have seen here. What was this result? This result we have seen in the previous lecture. Eigenvalues of two similar matrices are same, right? So A is diagonalizable. That means A is similar to the diagonal matrix. And if A and diagonal matrix are similar, then they will have the same eigenvalue. And the eigenvalue of the diagonal matrix, eigenvalues of the diagonal matrix are the diagonal elements of the diagonal matrix. Okay, so that means the matrix that you have formed in this example, the elements of the diagonal elements of this diagonal matrix should be the eigenvalues of A, and this is indeed true. So this is the diagonal elements of the diagonal matrix D, and this corresponds to the eigenvalues that you have obtained here. You see this? And this will be in the same order in which you have placed the eigenvectors. First eigenvector in the first column in in matrix P is the first eigenvector, and the first eigenvector corresponds to 0. So that is why you see that the first entry in the diagonal matrix is 0. Second eigenvector in P, second column in P is the second eigenvector, and second eigenvector corresponds to the eigenvalue minus 4. So you get minus 4 here. And the third column of P is the third eigenvector, and the corresponding eigenvalue is 3. So the third element of the diagonal element, the third of the diagonal is 3. So it is in the same order, right? जिस order में तुमने लिखा है x1, x2, x3, to form the matrix P, the diagonal elements will be in the same order. If you write this as the first column, so instead of defining P, if you define this, minus 1, 2, 1, 2, 3, minus 2, 1, 6, minus 13. So first column of this corresponds to which eigenvalue? Minus 4. Second column of this corresponds to which eigenvalue? 3. And the third column of this corresponds to which eigenvalue? 0. So when you form P in this way, then your diagonal matrix will be minus 4, 0, 0. This will be your first entry, first diagonal entry. 3 will be your second diagonal entry. And 0 will be your third diagonal entry. Right? So this order will be maintained.
Excuse me, sir.
Yes.
Sir, I wanted to ask, please bring it back to the previous slide.
Yeah.
In the matrix A, if we want to find the eigenvalues, so if we do the sum, the ones that like the sum is equal to the trace, the product is equal to the determinant, and taken two at a time, sum is equal to the leading diagonal cofactor sum. So if we do by that, three distinct eigenvalues we found by those three equations, so it will be wrong, or it is okay to be done like that in the paper.
Sorry, so what was your question?
I was saying that finding the eigenvalues by using the three equations of the sum will be equal to the trace and the product will be equal to the determinant.
So you want to
And
use these equations to find lambda 1, lambda 2, lambda 3.
yes, sir.
That you can do. But then your calculation will become complicated.
No, sir. Like if we find just those three equations and then we say that like hidden trial can be used after that, we all have to do it in a formal way.
You can calculate the values of the eigenvalues, lambda 1, lambda 2, lambda 3, lambda 4, but using this relationship, but it will complicate your calculation because first you have to find the determinant, then you have to find the trace, then cofactors, and so on. Okay.
Yes, sir. But
Size of the matrix is small, 2 by 2, then this calculation may be easier to do. But if the size of the matrix is big, 10 by 10, then not be that much easier.
yes, sir, that's true. Like I was saying that if we solve this, all of this, like a minus lambda I, and then we found the equation at last, we reach there only, like lambda cube minus trace of a lambda square, like that. So, by going by that from the starting, reduces some steps, like solving the matrix for the for the equation.
What is your final question? Because I think these are comments. So what is your final question?
I was just saying that if we use those three equations to find the eigenvalues, it will not be wrong with the paper. That is the
No,
only final
no,
question.
it will be a correct answer, but in the paper you have to save time also.
Okay, sir.
Right. So if you think that by analyzing the matrix, maybe if the matrix has several zeros, then you can do it quickly with this method. Maybe
Okay, sir.
with the same time. But if you start doing this using method, you will spend a lot of time for a calculation for which you will not be rewarded. You will not get any extra reward. You
Okay,
will do
sir.
a lot of
And
calculation, but no, with the same reward. Whereas you can get the same grade, same mark with less calculation.
and one more, sir, that
Hmm.
if we do elementary row operations on a matrix like this, given one, so the eigenvalues of the matrix that we obtain after the operation will be same
Yeah, similar
or not?
matrices will have same.
No, sir. I am asking about row equivalent matrix.
Row equivalent, then you have to see the determinant because the eigenvalues you calculate by this. If you interchange to row, the determinant will change.
Okay, so by doing that, it will
So
become wrong.
yeah, don't do any elementary row operations call out to find the determinant because you have to keep track of the signs and then maybe some constants you have to keep track of. You can do this like also mathematically, there is no problem with this, but then you have to keep track of all the constants, positive, negative signs, and this will make life difficult.
Okay, sir.
So straight away calculate the determinant the way you know how to calculate. Do not apply elementary operations there.
Okay.
Fine.
Yes, sir.
Any more question? Okay, so no question, so we proceed further. So as I said in the beginning that A has distinct eigenvalues is a sufficient condition for diagonalizable. That the converse may not be true. That means the matrix is diagonalizable, but the eigenvalues are not distinct. And this we will show with this example. So consider A. You calculate the eigenvalues of this. The eigenvalues will come out to be 5, 5. Now these eigenvalues are not distinct. You have two eigenvalues and they are same. Now you can calculate two eigenvectors corresponding to 5 so that they are linearly independent. So in this case, I think this example will fit here. So you have distinct eigenvalues and then you calculate the eigenvectors. The eigenvectors will come out to be in this form. Okay. So you get this equation for the eigenvector. And you have when y1 is equal to 1, x is equal to 2, and then the linear combination of this will be the eigenvectors. So you can say that there are infinitely many eigenvectors, but they are not linearly independent. And since eigenvectors are not linearly independent, therefore A is not diagonalizable. Because if A is diagonalizable, eigenvectors must be linearly independent. And converse also holds. If eigenvectors are linearly independent, then A is diagonalizable. Okay. Now we have another example where we see that the eigenvalues are lambda 1 is equal to -1, lambda 2 is equal to 1, and lambda 3 is equal to 1. Now these two values are repeated. Okay. Now let us see whether we can say that A is diagonalizable or not. So here we calculate the eigenvector corresponding to the eigenvalue lambda 1 is equal to -1. Let's say this comes out to be this. And corresponding to the eigenvalue 1, the eigenvector satisfy this equation. -x plus y is equal to 0 and z is arbitrary. Okay, so what we can do is we can take two vector, this one and this one. These two eigenvectors are linearly independent and they satisfy this condition also. Z is arbitrary. You can take z is equal to 1 and x and y 0, 0, or you can take x is equal to 1, y is equal to 1, and z is equal to 0. These two eigenvectors are linearly independent. One can easily check that the dot product of these two vectors is 0. So they are linearly independent. So that means we are able to find three eigenvectors. We are able to find three eigenvectors. What are those eigenvectors? We have this one, we have this one, and we have this one. These three eigenvectors, and these three eigenvectors are linearly independent, right? So we said that if the eigenvectors are linearly independent, then you can say that A is diagonalizable. So here we can say that A is diagonalizable. And in it, you can find the matrix P by arranging these eigenvectors as the columns. So you put this as first column, this as second column, and this as third column to form the matrix P. And then you can check P inverse AP is equal to D, where D is the diagonal matrix with elements as the diagonal values in the same order. So first column of P is x1, and x1 corresponds to the eigenvalue -1, so you have -1 here. And the remaining two columns of P corresponds to the eigenvalue 2, eigenvalue lambda. So this appears here, lambda and eigenvalue 1. So this 1 appears in this here. Right. So that this shows that the distinct eigenvalues lead to a diagonal matrix, lead to a diagonalizable matrix is just a sufficient condition, not the necessary condition. So here we have seen that if we have seen that A is not diagonal in the first example, we have seen that A is not diagonalizable and the eigenvalues are equal, not distinct. And in the second example, we have seen that A is diagonalizable and the eigenvalues may be equal. Two eigenvalues are equal. Okay, so this is not a necessary condition. Fine. Any question here? Once again. Okay. Okay. So now some notes. So recall from these slides that Ax is equal to 0, where x consists of n unknowns and A consists of m linearly independent rows. That means the rank of A is m. The number of linearly independent solutions of this will be n minus m. You can assign some n minus m variable as free variable and then solve the equation. Okay. So from example 17, we have corresponding to the eigenvalue lambda is equal to 2. We have the rank of A minus lambda, A minus I is 1. Therefore, there are two linearly independent solutions. So this is just a revisit of the things that we have done. So you can read this. Just some points in bullets I've written this for you to keep these points in mind. And then you have this homework that you can do. So now this third point is that diagonalizable matrix may not be invertible, and this is obvious because we say that A is diagonalizable. You just consider a diagonal matrix like this 1 0 0 1, or any diagonal matrix with with at least one diagonal element as 0. So diagonal matrix is similar to the diagonal matrix, similar to itself. Diagonal matrix is similar to itself, so therefore every diagonal matrix is diagonalizable. Okay, so this matrix is diagonalizable, but it is not invertible. Okay. Now we have another important result here. Oops. So it says that if A is diagonalizable, then there exists a non-singular matrix P such that P inverse AP is equal to D. This is from the definition of diagonalizable matrix. Okay. My baby has started crying, so just wait for him to settle down. Sorry about this. He is only 5 months old, and 5 months old baby are unpredictable. They can start crying at any time. So sorry about this interruption. Okay, so I was saying that A is diagonalizable. That means there exists a non-singular matrix P such that P inverse AP is equal to D. Now, from this relationship, we can say that P inverse AP into P inverse AP is equal to D into D. Okay. So we have this relationship, and the left hand side